We talked about rotation matrices. Now let's talk about homogeneous transformations. In rotation matrices, we assumed that there was no translation, or rather translation did not matter. We were only concerned with components of a vector in two different frames with different orientations. Now let's also start worrying about, so you still have the 0 frame and the 1 frame, the first coordinate frame and the second coordinate frame with different orientations. The relationship between those two orientations, you can still use the same rotation matrix theory. But now we have an added complexity of there is also a translation in the origin. So there is an initial coordinate frame with an initial origin. It's translated to a new location and then rotated to a new orientation. Now if there is no rotation and you are concerned with, let's say, a point P in three-dimensional space, same as before, and you have a vector here, remember the vector P represented in terms of the components along x1, y1, z1 we were calling P1, and along the components x0, y0 and z0 we were calling P0. And if there was no rotation and we were taking into account the different origins, then we would get P0 is nothing but P1 plus D0 to 1. It's just this vector added to the other vector, right? This is relatively straightforward. With rotation, assuming, now this is an important assumption, assuming that D0 to 1 is a vector that is still expressed in terms of the components of the 0 frame. So I don't need to worry about changing the components in any way. This is already in terms of the components in the 0 frame. Then I would simply get D01 will still remain as it is, but P1, since it's now components in a rotated set of unit vectors, I will need to do the rotation matrix multiplication here to get it in terms of these components, right? This is only concerned with changing the components in terms of different orientations, and this part is making sure that the translation is taken into account, right? So very similar idea to rotation matrices, but now with the translation. Where it gets a little bit more complicated is when you have a sequence of such transformations. Now this translation plus rotation together is referred to as a homogeneous transformation. Now when we have multiple of these, so now I have P1 is equal to R1 to 2 P2 plus D1 to 2. I'm not drawing it here, otherwise it will be too complicated. There will be too much information on the board, but essentially if there was another translation and another rotation and then this P is still written in terms of the new frame, then this would be the relationship between P, coordinates of P in the new frame versus the older frame, right? Now if I think of, just like we did in rotation matrices, now if I think of a sequence of these and how do I relate the newest set of coordinates to the first set of coordinates or the base frame, right, the initial frame. Now again here mathematically it's easy to figure out because I simply plug in P1 over here and then see what I get. So let me substitute P1 over here, and that gives me P0 is equal to R0 to 1, and in here I get R1 to 2 P2 plus D1 to 2 plus I still have my D0 to 1 outside, right? So I would get R0 to 1 multiplied by R1 to 2 P2 plus R0 to 1 D1 to 2 plus D0 to 1. Now, even though this looks a little bit more involved, actually it's not that complicated. What's going on here? There were two orientation changes, and these two rotation matrices multiplied in the right sequence is really accounting for the two orientation changes, and it's exactly the same as what we saw in rotation matrices. The only difference is now there are two translations. The first translation was still expressed in terms of the zero frame, so there is nothing to be done to that translation. The second translation was assumed to be expressed in the first frame. Right, so now I have to use the rotation matrix to express the components of that translation vector in the zero frame, and that's what is happening here. So really this is still all translation, but this translation is just expressed again in terms of the zero frame, and this is all rotation. So what I would do is write this as P0 R0 to 2 P2 plus this whole thing is D0 to 2. Now, just like in rotation matrices, we could set it up as sequence of matrix multiplications. We can do the same thing over here, but we need to add a little bit of detail here to do that. To make the homogeneous transformations work as a simple matrix multiplication, we need to add a little bit of detail, and all we need to do is for each of these vectors we need to add an artificial one, and if we do that we can write this whole set of operations as really an R D01 multiplied by P1, again an artificial 1 added. So if you multiply this out, you can see that you will get this pattern, and if I keep doing this over and over again, so this is P01, and this matrix is my homogeneous transformation matrix multiplied by P1, 1. And I can now string together a sequence of homogeneous transformations and simply construct this matrix for each of those transformations and multiply them together in the right sequence. The only thing I need to remember is my coordinates. I add an extra artificial 1 at the end, then I multiply them out, and whatever I get in the end, I ignore the last one, and what the first three numbers that I would have would be the coordinates in terms of the zero frame. So using this framework, again, I can automate any number of homogeneous transformations that account for both orientation changes and translations. And as we saw in the robot, at each joint you have a link length which translates your coordinate frame, and then the motor rotation can give you an orientation change.